This is the second part to the 1.2 video, and we are going into triangles. So, an important property of triangles deals with the sum of the measures of the angles of any triangle, meaning that if we took any triangle and we added up the angles, we would get 180 degrees. So that means we only need to know sometimes just two of the angles and we can tell what the other ones are. Sometimes we only need to know one of the angles and we can find out what the other two are. It just kind of depends on the kind of angle. So if we have a triangle that looks like this, and this is example 2, and we know this is x, and this is 61, and this other one here is 48, it's real easy to find out what x is because you know 48 and 61. But what I'd like to do right now before we get too far into this is get you familiar with the different types of triangles that we're going to be dealing with. So here we go. This is from your book. An acute triangle is any triangle where all of the sides are less than 90 degrees. So it gives you one right there. A right triangle is one where one of the angles is 90 degrees, or a right triangle. Obtuse means one of the angles is greater than 90 degrees. An equilateral means that each of the sides are congruent. That's where the lateral comes from. It has to do with the length of the sides. Equiangular, which isn't on here, would mean that not the sides are concerned, but we're talking about the angles being equal. Which if the angles are equal, the sides also have to be equal. An isosceles triangle is a triangle where two of the sides are equal in length. And what happens is if these two sides are equal in length, then the two angles that connect the other side are going to be equal in length as well. And a scalene triangle is a triangle where none of the sides are the same length. They're all three lengths different. So equilateral, all the three sides are the same. Isosceles, two of the sides are the same. Scalene, none of the sides are the same. In triangles that have the same shape and are the same size are called congruent triangles. That means that everything about them is the same. You will get into some triangles that are proportional to each other, but they're not congruent. One may be smaller than the other, but if they're not congruent and everything else is the same, then they're what are called similar. So if the angles are the same, they're just bigger and smaller. So for example, now that I got myself into that, I better explain it. If I have a triangle like that and a triangle like that, and the angle, this angle is the same as that angle, this angle is the same as that angle, and this angle is the same as that angle, then they're called similar triangles. So anyway, let's look at conditions for similar triangles. It says corresponding angles must have the same measure, which I just said. The green ones are corresponding. They have the same measure, the blue ones and the red ones. Corresponding sides must be proportional. That means that this corresponding side, I'll do this in green, is proportional to this one, and this one is proportional to this one, and this one is proportional to this one, and we'll get into the proportion part of it in a few minutes. All right, so let's look at example number 3 here. Get rid of some of my stuff. Example 3 says in figure 19, triangles ABC and NMP are similar. Being similar means that the angles are the same. Does not necessarily mean that the segments, the sides are the same. Find the measures of angles B and C. Okay, so what we're looking for is this angle and that angle. We're looking for B and C. Well, since the triangles are similar, corresponding angles have the same measure. So I know that C and P are going to have the same measure, and I know that B and M are going to have the same measure. Now notice here, what we've got, let me erase my circles. What we've got is, see, I've got 3 lines here, and I have 3 lines here. That is to tell you that this angle and this angle are the same size. Here I have 2 lines, so I look over here for another one with 2. That tells me that C and P are the same. And this one has 1, and that one has 1. We do that with lengths too. So if I said this, and this, and I just put 1 line across each, that means that the line lengths are the same. They're not in this one, so I can't say that, but if I did put that little mark through that, whether it looks like it or not, I'm saying that they're the same length. So that's what those little marks mean. Let's see, example 4, finding side lengths in similar triangles. So let's go ahead and do that. So we did this last year. In fact, we did it kind of at the beginning of the year, so it's very easily forgotten. But what we're doing is we're trying to find the lengths of these similar triangles. Now, how do I know they're similar? This angle has 2 lines, this one does. This one has 1, this one does. This one has 3, that one does. If that's the case, then I know that they're similar. And if they're similar, that means the lines are proportional. Remember a few minutes ago I was talking to you about proportional? Well, this is one of those instances. So what they're trying to get us to do is find out the length of this, DF, and the length of EF, given the information. I'm given the length of these 3, and I'm given the length of that. So which one do we want to find? Let's go ahead and find this one first. Let's just call it X, okay? That would be the length of DF. So what I'm going to do is 16 is to 8. 16 is to 8 as 24 is to X. So what I'm doing is I'm showing proportionality. So 16 is to 8 as 24 is to X. Then I cross multiply and I solve for X. You could also do it a different way. I could do 16 is to 24, so I'm keeping this one triangle together, equals, and then I use corresponding. 8 is to X, so I keep these 2 together and separate them by an equal sign. And then I cross multiply. You get the exact same answer because notice I'm multiplying 16 times X, 16 times X, 8 times 24, 24 times 8. These 2 numbers are just switched places. Doesn't really matter. I like using this method right here because what I do is I look at the 2 numbers in this triangle, 2 in this triangle, and I know that there's an equal sign between them. And it just makes it real easy for me to go ahead and solve that. You do the same thing. Let's see if I can erase some of this stuff. When you're looking for the other side of this one triangle that we're dealing with here. See if I can get rid of a bunch of that stuff. Okay, so let's see if we can find the length of that. Let's call that one X. So, do the same thing again. 16 is to 32 as 8 is to X, and you cross multiply. So see what I did? 16 over 32. I could have written 32 over X. It wouldn't have mattered. 16 over 32, but then when I write this, I have to make sure 16 is on top here, 8 is on top here, because these are the corresponding sides. Corresponding sides have to be on the same level when you do the proportions. And that means that the 32 here is on the bottom, this is on the bottom. Now, like I say, I could have written this as 32 over 16 equals X over 8. Wouldn't really matter because, again, 16 times X, 16 times X, 32 times 8, 32 times 8. Doesn't really matter what order I do those in. All right, let's jump to example 5. One of the things that you can do in example 5 is you can determine how tall things are based on other things. So, for example, if we want to know how high this flagpole is, this distance, this distance between here and here, we can do that by knowing some other parts of it. Now I know this is 10 and this is 18. So I'm just going to use my whole ratio thing. 10 is to 18 as What's the corresponding line with the 10? It would be what we're looking for right there. X is to, what's the corresponding to the 18? 99. Cross multiply, 990 equals 18x, and go ahead and solve that, and you'll find out that x then is 55. So you've just determined that flagpole is 55 feet high. Okay, so that is it for lesson 1.2. The next video will have to do with the problem set.